So this is wrapping up Unit 1. So tomorrow is your Unit 1 test. We're going to talk about factors. Factors are numbers that will divide evenly into other numbers. For example, factors of 12. Well, 2 divides evenly into 12 with no remainder. 3 divides evenly into 12 with no remainder. 4 does, and so does 6. Now I get asked every time, well, what about 1? 1 divides evenly into it. Yeah, 1 divides evenly into anything, so therefore we don't count it. The other one would be, what about 12? 12 divides into itself. Well, if you divide it by itself, the result is 1, so therefore we don't count it. Anything is divisible by itself. And dividing it by 1 or itself really doesn't simplify things any, so we don't count those as factors. A lot of times we get something called factor pairs. So again, this is for factoring 12. I could have 2 times 6 or 3 times 4. I could, if I really wanted to get technical, I could do negative 2 times negative 6, whatever. We're going to just stick with positives for right now, because the negatives mechanically are not very useful unless we get into algebraic factoring. However, if I request that you factor 12, how do you know which one of these I want? Well, the answer is you don't know. So generally what we do, rather than doing factor pairs, is we do something called prime factoring. Instead of breaking it up into pairs, we actually break it up into the smallest possible numbers we can. So if I'm going to factor 12, we do what's called a factor tree. So I look for what is any number that's a factor of 12. Okay, 2. And then 12 divided by 2 is 6. So 6 is left over. 2 is what we call prime. A prime number has no factors. In other words, the only things it can be divided by are 1 and itself. At least the only whole numbers it can be divided by are 1 and itself. Of course, you're going to be divided by some decimals and fractions and stuff. 2 is a prime number. There are no smaller numbers other than 1 that can divide into it. Of course, other numbers are called composite. If you think of like composite materials are made up of other lesser materials put together. You know, like polymer composites or plastics, and a lot of times embedded ceramics, or even wood in plastic composites. So composites have factors. They have smaller components that go into them. Well, we're going to come back and finish that now. So we've split up the 12 here into 2 and 6. The 2 is prime, so I'm going to circle it. The 6 is composite, meaning it does have smaller factors. What's one of them? 2. And if I take 6 divided by 2, I'm left with 3. 3 is also prime. So I have broken the 12 up into prime factors. There are no smaller numbers that I can break that into. So 12 is 2 times 2 times 3. That's the prime factoring of 12.
What if we did 3 and 4?
What if we had done 3 and 4? So you got 3 and 4. The 4 splits up into 2 and 2. Now I always put them in order from smallest to largest is the proper etiquette. I mean, it's not incorrect if you don't. It's just more proper if you do. In fact, some books will list it like this. 2 squared times 3, because there's 2 2's. So We have prime numbers, composite numbers. Just to kind of a quick run through before we do more prime factoring. 11, prime or composite? So that makes it prime. 14, prime or composite? Composite. 17, prime. 27, composite. 29, prime. 31 is prime. Nothing divides into 31. 37, nothing, so it is prime. 39, 3 and 13. 41, prime. 47, prime. 49, yeah, 7 and 7. 51, (3 and 17). 57, (3 and 19). So, this leads us to the next little side topic here. Divisibility. Obviously, a number is divisible by its factors. Divisible means it divides without remainder. A lot of I's. So it divides with no remainder. As you saw going through this list here, it can sometimes be difficult to decide whether a number has factors, whether it can be divided by anything. So we're going to look at divisibility rules here. We're looking at divisibility rules. There are shortcuts for being able to look at a number and tell if it can be divided by another number. So, if I want to know if a number can be divided by 2, what's the shortcut? It's an even number. By even number, that means the last digit is 0, 2, 4, 6, or 8. So, 791,352, is that divisible by 2? Yeah. This last digit's an even digit. It's a 2, so that's divisible by 2. Everybody know the rule to tell something's divisible by 3? Some of the digits. What on earth does that mean? Well, let's say we've got this. 567,342. What's 5 plus 6? 11 plus 7. 18 plus 3. 21 plus 4. 25 plus 2. 27. Is 27 divisible by 3? Yeah. What if we didn't know that? Well, what's 2 plus 7? 9. Is 9 divisible by 3? Yep. That means 27 is divisible by 3. That means 567,342 is divisible by 3. We were working with 57 earlier. Wondering if it's prime or composite. What's 5 plus 7? 12. That's divisible by 3. So 57 is divisible by 3. The sum of the digits is divisible by 3. Then the number is divisible by 3.
So 57 would be 3 and
19. Now, to tell if something's divisible by 4, if we're doing prime factoring, it really doesn't matter. We can just divide by 2 a couple of times. So 4 is unimportant, and the rule for 4 is a little bit clumsy. The rule for 4 looks at the last 2 digits. So let's say I have 9,357,500. Everything I've written down so far doesn't matter. All that matters is the last 2 digits. Is 84 divisible by 4? Yes, so that whole number is divisible by 4. Now the problem with this is, how many of you have all of your multiples of 4 memorized up to 100? Not very likely, right? So if I gave you a number like 7,952, would you know if 52 is divisible by 4? It is, but you wouldn't necessarily have it memorized. So that is divisible by 4 as well. But again, kind of clumsy having to memorize all the divisors of 4. I mean, if you're quick, you divide 52 by 4 and it comes out to 13, but not the most convenient way of doing things. But again, it doesn't matter, because if you're going to divide by 4, you just divide by 2 twice and you get the same point. The next one's a little simpler. 5. Last digit is 0 or 5. So again, nothing else matters. All that matters, that's a 5. So the whole thing is divisible by 5. 6. Divisible by both 2 and 3. Looking at this number here, I have to decide if it's divisible by both 2 and 3. Now, I'm going to give you a little hint. I always look for the 2 first. Looking at this one, is this divisible by 2? No, because the last digit's not even. It's a lot quicker to see if it's divisible by 2. For 3, I got to start adding the digits together. Well, why bother starting to add the digits together when I can just look at that last one and say, hey, it's not divisible by 2. So until I know it's divisible by 2, I'm not going to bother adding the digits together. So that one is not divisible by 6. This one, is it divisible by 2? Yep, last digit's an 8, so it's divisible by 2. 4 plus 2 is 6 plus 1, 7 plus 9, 16 plus 8, 24. Is that divisible by 3? Yep, if not, 2 plus 6 is, or 2 plus 4 is 6, which is divisible by 3. So yeah, 24 is divisible by 3. The whole thing is divisible by 3. So it's divisible by both, so it is divisible by 6. Anybody know the divisibility rule to tell something's divisible by 7? I don't either. If one of you can come up with a rule that can determine if a number is divisible by 7 without actually dividing it out, show it to me. I'd be willing to give you extra credit. Hell, I'd be willing to give you an A for the class, because I'm going to go publish it and make some money off of it. That's how it works, by the way. Have you ever seen in academia, these major accomplishments? Usually it's a student that came up with it, and the professor took it and polished it up and wrote it up and published it, and they get the credit for it. Like the Pythagorean theorem, they figure was not developed by Pythagoras. Pythagoras ran a mathematical school in Greece, and they figure it was one of his students that came up with it, and he just polished it up and made it, common knowledge. But that's how things were back then, especially is if you worked under somebody, the person with the big name has got credit for it. 8. This one's not very useful either. Last 3 digits. So when we look at this, all that matters are these last 3 digits. Are those 3 digits? Is that number 464 divisible by 8? Well, again, how many of you have your multiples of 8 memorized up to 1,000? That is divisible by 8. But again, it's just as easy to punch in the calculator. You're almost going to have to punch the 464 into the calculator, divide by 8 to make sure it comes out. At that point, why don't you punch the whole thing in? I'm not a huge punch into the calculator fan, but there are certain things it's just more practical for. 9. Same rule as 3, sum of digits. Now again, you could just divide by 3 twice, but this one actually does work out pretty well. So 25,731. What is 2 plus 5? 7 plus 7, 14 plus 3, 17 plus 1, 18. Is 18 divisible by 9? Yep, so that whole thing is divisible by 9. How about 10? Last digit is 0. Now you already saw, I said that 8 doesn't really matter. You just divide by 2 3 times. The 4 doesn't matter. You can divide by 2 twice. 6 doesn't really matter. You can divide by 2 and then by 3. So really the important ones here so far are the 2, the 3, the 5, and the 10. If I'm looking at a number, I usually look for 10 first because it's really simple. Doesn't end in a 0. Then I look for 5 because if it didn't end in a 0, it doesn't end in a 5. Then I usually look for 2s because, again, all I'm doing is looking at that last digit. And then I look for 3s, and I start adding the digits together, see what I get. There are divisibility rules for bigger numbers. Now, they don't need one for like 12 because 12 is 2 times 2 times 3. You divide by 2 twice and 3 once. 15, you divide by 3 and then divide by 5. So they only tend to do divisibility rules for prime numbers. And there are several of them. The problem is, as you get larger than 10, and so the numbers themselves get larger, the divisibility rules get more complex. As an example, I'm going to show you the divisibility rule for 11 right now. I don't expect you to write it down because I'm never going to ask you to do it, but it is kind of complex. What it involves is taking every other digit. So let's just put a number up here. So 732,500 and 40. What do I want to put on here? We'll go 45. So what you do is you start with the first digit, and then you take every other digit. You add those up. 7 plus 2 plus 4 is 13, right? Yeah. Then take the other digits. They're left. Add them up. 3 plus 5 is 13. Then you subtract. If the difference is either 0 or divisible by 11, the whole number is divisible by 11. So 0, 11, 22, 33, That was pretty complex. At that point, you're probably just going to punch it in the calculator. And like I said, there are some for 13, 17. There are others as you go up the ladder. It's just they get so complex they're just not really worth memorizing. I don't even have those memorized. I have memorized the 11 just because I have an example to show you how much they suck as the numbers get bigger. That's about it. Why do we care about factoring? Well, there are some things we can do with factoring. Remember, we talked about factors are those numbers that go into another number, divide in. So factors are smaller numbers that divide into the other numbers. So I might look for something called greatest common factor between two numbers. Which of course abbreviates GCF. Greatest common factor between two numbers can be found by factoring. Let's say I want to find the greatest common factor between 72 and 60. I'm going to factor them. So I'm going to start with 72. What's one number that goes into 72? 9. 72 divided by 9 is 8. Neither of those is prime. 9 can be split up into 2 times 3. Both of those is prime. 8 can be split into 2 times 4. 2 is prime. 4 splits into 2 and 2. So that gives us 2 times 2 times 2 times 3 times 3. Now we got the 60. Oh, and then the 0 can be divided by 10. So we're going to go 10 and 6 first. 10 splits into 5 and 2, both prime. 6, 3 and 2. Or 2 and 3, both prime. So 6 is 2 times 2 times 3 times 5. Now the greatest common factor involves all common factors. So there's a 2 in common. There's another 2 in common. And there's a 3 in common. So I've got a 2, and a 3. If I multiply those together, I get 2 times 2 is 4 times 3 is 12. 12 is the greatest common factor, the largest number that divides into both 72 and 60. Very handy for reducing fractions and all sorts of other things that we use them for. A multiple are the numbers that result from multiplying a number by 1, then 2, then 3, then 4. So if I give you 7, right? The multiples of 7 are 7, 14, 21, 28, 35, blah, 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 blah. All right? You keep going. Multiples, as you can see, are either at least the size of the number or they are bigger. They're never smaller than a number. Least common multiple between two numbers, otherwise known as the LCM. So we got GCF, greatest common factor, LCM, least common multiple, is made up of all factors. So if I want to find the least common multiple of two numbers, let's say we have 12 and 18. We are going to factor. 12 splits up into, let's go 4 and 3. We go 2 and 6, it don't matter. 3 is prime, 4 goes into 2 and 2, both prime. So 12 is 2 times 2 times 3. 18 divides into what? 9 and 2. 2 is prime. 9 is 3 and 3. Both prime. So 18 is 2 times 3 times 3. Now, unlike the greatest common factor, we were taking all the common factors and just multiplying them together. Here, this is least common multiple. The least common multiples contain all the same pieces. So we look for what's missing. So this has, they each have a 2. We find the ones that are in common. They both have a 2. And they both have a 3. But you notice there's stuff that isn't circled there yet. Those are the ones that are not in common. This one has a 2. This one does not. So we're going to have to multiply that by 2. Now they both got a 2. Does that make sense? The second 2. This one's got a 3. This one does not. So I'm going to multiply this one by 3. Now they both have a second 3. Now 2 times 2 is 4. Times 3 is 12. Times 3 is 36. 2 times 3 is 6. Times 3 is 18. Times 2 is 36. 36 is the least common multiple of those two numbers. So all you're doing is finding what factors are missing. So in your notes, I want you to try this, see if you remember. Find the greatest common factor of 20 and 30, and then find the least common multiple of 20 and 30. I'm going to give you a couple minutes. Okay, either way we're going to have to factor. When you factored 20, what'd you get? 2 times 2 times 5. Very good. So I'm just going to fill that in on both problems because, well, the factoring of 20 is the same no matter what we're doing, right? How about 30? 2 times 3 times 5. Now for greatest common factor, am I just looking for the ones that are in common, or am I looking for the ones that are missing?
Most common.
Yeah, it says most common. So I've got a 2 and a 5. 2 times 5 is 10. 10 is my greatest common factor. Remember, a factor is always smaller than the number. A factor has to go into the number. So 10 divides into both 20 and 30 without remainders. It is the largest number that divides into both 20 and 30 without remainders. Now for least common multiple, I still look for the ones that are in common. But I don't stop there. I look at what's left over. The top one has a 2 that the bottom one does not have. So I give the bottom one a 2. Bottom one has a 3 that the top one doesn't have. So I give the top one a 3. Now everything's in common. That's 60. That is 60. 60 is the least common multiple. It is the smallest number that both 20 and 30 will go into. Where the factor goes into the 20 and 30, multiple, the 20 and 30 go into it. So the multiple has to be larger than both of them. The factor has to be smaller than both of them. In your book on page 26, it is 1 through 63, the odds. Remember, tomorrow is Unit 1 test. You can feel free to cheer. It's okay. I allow you to celebrate.